Okay, now that we've practiced taking the derivative of both sides of an equation with respect to t, again, we haven't done much with that equation yet, but we're going to see how this idea applies to an applied problem. Oops, my y equal y of t is stuck to this part. Sorry about that. All right. Whoops. Okay. Our example right now is air is being pumped into a spherical balloon. Here's the picture of the balloon at a rate of 20 cubic inches per minute. How fast is the radius of the balloon increasing when the radius is 6 inches? Okay, so this is an example of a related rates problem. Okay, so we're going to skip this first question here, read the problem carefully, and identify the type. I want to just go straight to identifying the quantities that change. Let's go back, maybe do some talking to the text. We're going to read the text, we're going to write what we're thinking as we're reading it, and that will help us make sense of what's going on. Okay, so air is being pumped into a spherical balloon. Okay, so I see a picture of a sphere that's already provided for us, but maybe in future problems I'll have to do that myself. At a rate, okay, so rate has to do with derivative. Because derivative is slope, slope is a rate of change. This is one of the main applications of the derivative, rate of change. Not just finding the slope of the tangent line, as I keep telling you, but it's also used in a lot of real life situations to talk about rate of change of quantities. Okay, so the rate is 20 cubic inches per minute, 20 inches cubed per minute. Okay, so inches cubed is a measure of volume. So volume per unit of time is what we see here. All right. So now I see a question word, how fast, or a question phrase, how fast. So how fast, so it's asking now for a rate, asking for a rate. How fast is the radius, that must be this R in the picture. How fast is the radius of the balloon increasing? Increasing is probably important when the radius is 6 inches. Okay, so if it looks like they're calling the radius R, so we have, if we're going to answer this question of what what quantities are changing, we have R, which is the radius, and we have, I'll call it capital V, which is the volume, and then we'll call time T. Okay. Number 3 here is asking, identify the rates that are known and what is to be found. Okay, so let's see. So there's a rate here, a rate of 20 inches cubed per minute, which is volume. And it's a rate of change of volume with respect to time. So we know dv dt, which is the derivative of volume with respect to time. In other words, the change in volume with respect to the change in time. That number is going to be 20. And if you want to put units on it, it's 20 inches cubed per minute. Okay. Question is, how fast is the radius increasing? Okay, so it's asking for a rate. Which rate is it asking for? It's asking for the rate of change of the radius. And again, the radius is changing with respect to time. So the what is to be found is dr dt. We don't know what that is. Okay. something important to note is they're telling us to figure this out when the radius is 6. Okay, that's this part over here at the top. So let's see, how can we write an equation? I'm now looking at number 4 here. How can we write an equation that relates the variables? Okay, we have to remind ourselves of a geometry formula. That's the volume of a sphere, which we'll review over here. So the volume of a sphere is 4/3 pi r cubed. For those of you who will eventually go into Calc 3, you'll find out the calculus reason why that's the formula. But this is the formula you're taught in geometry class in your earlier education. So I think that's the equation that they want us to work with. Okay. Now number 5, differentiate the equation with respect to time. So I'm going to do what I did before in the previous slide or the previous video. I'm going to take d dt of both sides of this equation. Now I'm going to ask you to pause the video and practice some more with this idea. And again, you're remembering that v and r, we're assuming these are functions of time. And this makes sense in the problem because we're talking about volume and the radius changing as time changes. So pause the video, finish this differentiation of the equation, and then unpause. Okay, so you should have had a chance to do the differentiation, compare what you did with what I'm about to do. So you have on the left hand side dv dt equals well, let's see, 4/3 pi is just a constant, so I can take that out and put it in the front, and I end up with d dt of r cubed. Okay, so this is the part here that is going to be very similar to what we were doing in the warm-up questions. Continuing over here, I have dv dt equals 4/3 pi times 3r squared. But remember, this is a related rates problem. There's implicit differentiation chain rule happening in the background. So we have to multiply by the derivative of r with respect to t, which again we call dr dt. Quick note, don't say dr over dt. We're not thinking of this as a fraction. It's a derivative. We took the derivative operator d dt and we applied it to r. So it's slightly different from a normal fraction. All right, so what do we have left now? When we do this, we have, well, these 3's, we have a 3 on the top and a 3 on the bottom, so those are eliminated, and then we have dv dt equals 4 pi r squared dr dt. Okay. All right. We're almost done with this problem. So I'm gonna move up and, oops, our friend y equals y of t is left over from before. It got stuck to this piece. Sorry about that. So let's finish up this problem using the equation that we just got. It says substitute appropriate values and solve for the desired quantity. Desired quantity would mean the thing that is to be found, or what the problem asks for. So the problem asks for dr dt, which means in this equation, the only quantity we shouldn't know is dr dt. We should know all the other quantities. All right. So take this equation and try to plug in wherever you think the quantities we've identified, try to plug those in where you think they should go in this equation. So again, take a moment, pause the video, give it a try. Okay, so what you should have gotten is something like the following. dv dt we saw was 20, so I'm going to plug in 20 for dv dt on the left hand side. The 4 pi r squared is just left over. Well, sorry, the 4 pi is just left over from the right hand side. Those are just constants. R squared, I should plug in 6 for r. So I should have 6 squared. And then I have the dr dt, which is the quantity we don't know, the desired quantity. Okay, so when I work this out, I should get, let's see, 20 equals 36 times 4, which is, what's 36 times 4? Well, you could do it on a calculator, but I'm going to be old-fashioned for a moment. Okay, so it's 144 pi dr dt. Taking this and solving for dr dt, I have 20 over 144 pi equals dr dt. And I can clean this up a little. I can divide by 4 on the top and the bottom. And if I do that, I'm going to get 4 over 36 pi. Oh, wait. I can actually simplify that more. So now I have 1 over 9 pi equals dr dt. But what does this number mean? How do I interpret this number? It's saying how fast is the radius increasing. So this is a rate. Let's try to put the units on it. So our final answer would be that dr dt is equal to 1 over 9 pi, let's see, what's our unit of distance? I think it's inches, since our volume was inches cubed, so it's inches per, and our unit of time is minutes. All right, this is our final answer for this problem.